Section 2.5, Limits at Infinity. Let's start off with the definition, and then we'll kind of talk about what that means in notation and in terms of a picture. If f of x becomes arbitrarily close to a finite number L for all sufficiently large and positive x, where x is growing without bound, then we write the following. So there was the definition. Kind of hard to follow that, I think. But what we're saying when x is growing without bound, we're saying we want to look at the limit as x is going towards infinity. And then we want to see what's happening to the y value of that function. And if it's settling down to some fixed number L, the further we go out or the bigger x gets, then we say that that is the limit as x goes to infinity. And then similarly, if f of x approaches the number m as x decreases without bound, so now we're looking at the idea of x going to negative infinity when we say it decreases without bound, then we'd say we're looking at the limit as x approaches negative infinity of f of x. And if the y values are getting closer and closer to this number m or approaching that, then that would be the value of the limit. So we're going to start finding two new kinds of limits. What happens as x gets really big on the positive side or big on the negative side, instead of looking at x approaching some fixed number. So we can kind of see that on our graph here. If we're looking at x getting bigger and bigger, we're going out this way. And if the graph is settling down to a height, that height would be the limit. And if you're going the other direction towards the negative infinity side and that graph settles into some height, that height would be the limit. And that height also, as you can see with the dotted line that is already drawn there, which I'll emphasize some more, if there's some dotted line height that is approaching, then that horizontal line would be a horizontal asymptote. So if one or the other is satisfied, and what are we talking about, one or the other? If the limit as x approaches infinity is settling down to a number, or if the limit as x approaches negative is settling down to a number, if either of those is satisfied, then y equals L or y equals m is a horizontal asymptote for the graph. And the most common situation is that you're approaching the same number on both the right and the left, but not all functions follow that. So typically when we have a horizontal asymptote, it's for the right and left side of the graph. But as we continue on and see different examples, we'll see some where that's not true. Now, when we look at the limit as x goes to infinity or to negative infinity of a function, you could also say that what we're trying to figure out about that function is what's going on at the ends of the function, or what is the end behavior of the function. So when we look at these limits at plus or minus infinity for the x approaching plus or minus infinity, we're trying to get a sense of end behavior. So let's start looking at some different situations that are going to be common and learn how to deal with those. What happens to a fraction as the denominator gets very large if the numerator is held constant? So we're going to look at an example where we're inspecting the limit as x approaches infinity of 3 over x squared. So the top is held constant at 3, and the bottom is going to infinity and getting squared, which makes it kind of grow even faster. So the denominator is getting really big, and the numerator is held fixed. So what happens? So one way to kind of investigate what happens is to make a table. So we want to look at different values of x and what is happening to the values of 3 over x squared for those x's. And we're looking as x goes to infinity, so we could start with the number 1, which isn't very close to infinity, and then go to 10 and 100 and 1,000 and so on, and keep plugging in bigger numbers for x, which is that idea of it growing without bound, and then see what happens to the output. So the easiest way to do that is switch over into the calculator. So let's go look at all those different values real quick. So I'm going to start off by taking the number 1 and just pressing enter. As I've shown you in previous videos, that stores the number 1 in answer. And then instead of typing 3 over x squared, I'm going to type 3 over answer squared. Answer is above the negative key in orange, so I just hit the orange second key, and now I'm hitting the negative key to get answer, and I'll add the square. 1 is stored there right now, so when I press enter, I get 3 over 1 squared, and the answer is 3. Now I'm going to take the next number they wanted us to put in, which is 10, press enter, now that's stored in answer. So when I hit second second enter, and second enter again, I get back that 3 over answer squared, but now 10 is stored there, so if I press enter, I'm plugging 10 into my function, and I get 0.03. So my outputs went from 3 to 0.03. What happens if I put in 100? So second enter, get that 100. 3e negative 4. That's scientific notation, and it means 3 times 10 to the negative 4, or move the decimal left 4 places. Let's go ahead and write these down, and I'll decode that one for you. So we got 3 for the first one. We got 0.03 for the second one. For the third one, we got 3e negative 4, which means 3 times 10 to the negative 4th, which is the same as 3 over 10 to the 4th, which if you divide it will move the decimal left 4 spots, and we get 0.0003. Kind of a neat little thing that dawned on me at some point in my life is if you have 3 times 10 to the negative 4, that 3 ends up in the 4th decimal spot. So that's kind of a quick way to do it. You're going to put zeros until you get to your 3, which should be in the 4th decimal spot, matching those two pieces up. So 0.0003, and we have one left to do, so we'll bounce back over to the calculator, plug in that 1,000, press enter, so now that's stored an answer. Pull up my expression again so that I'm plugging 1,000 in, and I get 3e negative 6. So now, that time, it means that the 3 is going to be in the 6th decimal place. So I have 1, 2, 3, 4, 5 zeros, and in the 6th place, I'll get a 3. So I would argue that it looks like, kind of jammed up here, so I'll write this again. It looks like the limit as x approaches infinity of 3 over x squared. What's happening to these values? They're getting smaller and smaller and closer to 0. So it looks like the limit there is 0, and so I would say it looks like y equals 0 is a horizontal asymptote for the graph. Let's go ahead and look at the graph real quick on the calculator too to get that visual. So I already entered that function in, y1 equals 3 over x squared, and then we'll hit graph, and it really does look like we have a horizontal asymptote at y equals 0, and as we go further and further to the right, it looks like the graph is flattening out, getting closer and closer to the x-axis, which has a height of 0. And if I go to negative infinity, by the way, seems like the same thing's happening, still approaching a height of 0 on either side. And if we zoom out on that, then when we trace, we're plugging in bigger numbers, and you'll see we keep getting smaller and smaller answers. You start to see the scientific notation come up for the y values in the upper left-hand corner. By the way, if you want to snap back to that negative 10 to 10 window that I started with, I mentioned this on the TI-84. There's the zoom standard. It's on this calculator too. In the bottom left, I can press zoom, and then Z standard right here gets me back to negative 10 to 10 in both the horizontal and the vertical directions. But there's the graphical view of what we just did with the table, and it really seems like the heights are approaching 0 the further we go out to the right or to the left. So back to the notes, make a couple comments on that. It turns out that's going to always be true. If your value of k is positive, then the limit as x goes to infinity or negative infinity of a over x to the k is going to be 0. So either way, whether you're going to positive infinity or negative infinity, you still end up getting a limit of 0 if the top is a constant and the bottom has a value of x that is growing bigger and bigger and bigger. All right, let's go ahead and continue on and practice with some more examples where we're looking at the limit as x goes to either infinity or negative infinity and trying to apply what we just learned on the previous page. So for this one, we have the limit as x goes to infinity of the quantity 7 plus 5 over x plus 9 over x squared. So the first thing I would want to do is use one of those properties of limits that we got on a previous page and break this limit up into 3 pieces. So we can take the limit as x approaches infinity of 7 plus the limit as x approaches infinity of 5 over x. So we're just doing each term as its own limit. That was one of our properties of limits. And then we'll just evaluate those one at a time. So if you take the limit as x approaches infinity of 7, the limit of a constant is that constant, so we get a 7. And then the limit as x goes to infinity, if you have the top is a constant and the bottom is going to infinity, then the overall limit of that piece is going to be 0. And then if we go to the next one, we have the top is a constant, the bottom is an x to a power where x is growing to infinity, so that one would also be a 0. So we end up with just 7 plus 0 plus 0, so we just end up with 7. All right, so let's look at another one. This one's a little different because the top is not a constant. So we're looking at the limit as x goes to infinity of sine of 5x over x squared. And our numerator is sine of 5x, so it's not a constant. It's a function that's changing values. So we can't quite apply exactly what we learned on the previous page, but what we could do is try and take what we learned on the previous page and the squeeze theorem or the sandwich theorem and see if we can use that to try and see what's happening here. So let's start off with something we know about trig functions, specifically about the sine function, that the value of sine of 5 over x is always going to be somewhere in between -1 and 1. And then x is going to infinity, which means that x is going to positive infinity. So that means we're thinking about positive values of x's here. So I can divide all three parts of this by x to the fifth. And that will be dividing by a positive quantity, so it won't flip around or change the direction on any of those inequality symbols. So we would end up with -1 over x to the fifth is less than or equal to sine of 5x over x to the fifth is less than or equal to 1 over x to the fifth. So what's special about that? Well, the part in the middle is the thing we're trying to find our limit of. The parts on the outside are ones where the previous page applies because the top is a constant and the bottom is growing. So if we take the limits of all three parts, we'll know the answers of the outsides, and we can see if they squeeze the insides so that we can know that answer too. So we go ahead and take a limit of all three parts now. So on the left, we get the limit as x goes to infinity of -1 over x to the fifth, and that's less than or equal to the limit as x goes to infinity of sine of 5x over x to the fifth is less than or equal to the limit of the right side, 1 over x to the fifth. And then we just start evaluating what we can. So we can do this part because the previous page applies, and we can do this part because the previous page applies. So the limit on the left-hand side, we have a constant on top, x to the fifth on the bottom where x is going to infinity, so that limit is going to be a 0. We're going to stick with the idea that we don't know what's going on in the center because the top's not a constant. So I'll just copy that part down. But on the right-hand side, we have the limit as x goes to infinity where the numerator is a constant and the denominator's growing without bounds, so that part's also going to be a 0. So now we know that this middle piece right here, whatever this answer is, it has to be simultaneously less than or equal to 0 and greater than or equal to 0, and the only value it can have that does both of those things is 0. So by the squeeze theorem, by the sandwich theorem, we now can see that the limit as x approaches infinity of sine of 5x over x to the fifth is in fact equal to 0. So there's our overall answer to that. That's a little bit of work. I had to use the sandwich theorem and the previous page, but we still got there. All right, let's go ahead and switch gears a little bit and now start looking at what happens if both the y value and the x value are simultaneously both becoming very large. So if you look at graphs like parabolas right here, As x gets bigger, the y value is going upward too. So you would think that if that continues, that as x keeps getting bigger, y is going to keep getting bigger, and y will go to infinity just like the x does. If you switch over and you start looking at a fourth power, the same thing is true, only the y values grow even faster as you move out to the right or the left. And with y to the sixth, they grow even faster. So it looks like when you have an even power, 2, 4, 6, 8, and so on, if you were to look at what is happening to the function, what is going on with the limit as x approaches infinity of x to the n when n is even, it looks like, so we're talking about the right-hand side of these, it looks like they're all going upward towards infinity. So the x value is going to infinity, and when that happens, so is the y. And if you went to the left, so that you were looking at the limit as x approaches negative infinity of x to the n, where n is an even power, you still get the same thing, because as you're moving to the left, the y value is going up. Here, the y value is going up. The y value is going up, and up without bound and towards infinity. It changes a little bit if you do get n to be odd. So when you have these odd functions, now when you go to the right, the y value goes up, but when you go to the left, the y value goes down. And that's true for all the odds, whether it be, y to the third, y to the fifth, y to the seventh. They're all going to behave that way. So for those, we get a little bit different rule for the odd powers. The limit as x goes to infinity for x to the n on those is still infinity. But if you're going to negative infinity, since now the y value is going downward, those limits as you go to negative infinity of x to an odd power will be negative infinity. So thinking about this as n behavior on even functions, let's go ahead and get a different color just so we can get some new highlighting going. For the even functions here, on both sides, the y values are going upward. But when you do the odd ones, so if you have the fifth, the third, the seventh, then all the ones on the right are going up, but as you go to the left, they're all going down. So that's why we get this negative infinity when we go towards negative infinity. So that's the one different piece, is with the odd functions. So there's two different types of n behavior that we're currently looking at. So we have the n behavior from the previous page, where maybe is when you go out to infinity or negative infinity, the graph starts to flatten out. Or now we're saying this new option is maybe when you go to infinity or negative infinity, the function starts to either climb up towards positive infinity or dive down towards negative infinity. So we're going to use those ideas to continue to explore n behavior of functions. All right, let's go ahead and look at some more examples where we're looking at the limit as x goes to either infinity or positive infinity. Let's look at the limit as x goes to infinity of x squared minus 2x plus 7. I'm going to start out by trying to split up the limit and see what happens. So we'll take the limit as x goes to infinity of x squared minus the limit as x goes to infinity of 2x plus the limit as x goes to infinity of 7. I should be writing the x goes to infinity. I'm going to be a little lazy there and leave that off, but it's not going to change where we're approaching. And let's think about what each piece would be. The limit as x goes to infinity of x squared, according to the previous page, with an even power. You're going to get an infinity there. And then the limit of a 2x, that's also going to go to infinity. And then you would have the plus 7. So what's infinity minus infinity plus 7? And the answer is, not sure. You can't really say infinity and infinity cancel out, like the infinity minus infinity, because they're not necessarily the same size of infinity. Infinity isn't a specific number, it's this idea of a thing growing really large. So we have one really large thing minus another really large thing. They don't necessarily cancel. One might be larger than the other. So there's the temptation to say they cross off and you get 7, but we actually don't know what's going to happen because we don't know the relative size of these. So what does that mean? It means that that wasn't the right approach. So we're not going to go at it that way. We're going to go at it a different way. So here comes the different way. I'm going to take still the limit as x approaches infinity. But what I'm going to do is factor out x to the biggest power. So we had x squared, x to the first, and then a constant. So the biggest power I had was x squared. I'm going to factor that out. That leaves 1 minus 2 over x plus 7 over x squared. And I did that kind of quick, but you could check it to see that I did it right. X squared times 1 is x squared. If you multiply these two together, this x in the denominator right here would cancel one of those x's, and you'd be back to that x, and the 2 would still be there, so it would be a 2 over x. If you did this multiplication, this x squared would cancel the x squared, and only the 7 would be left, which is right there. So it looks like I did properly factor out the x squared. All right, so now what? Now we go back and start splitting the limit up some more. So we're going to say, let's take the limit as x goes to infinity of the x squared piece times the limit of as x goes to infinity of the rest of it, the 1 minus 2 over x plus 7 over x squared. So what happens if we do this? So let's start off looking at this piece. That piece right there is going to go to infinity, and then we'll look at what happens with this piece over here. So that first piece goes to infinity, and then in the next part, so you color coordinate all that stuff, this infinity is from the yellow part above, and then the part in green we'll figure out, like right here, what would go there. So the limit as x goes to infinity of the 1 is still the 1. The limit as x goes to infinity of 2 over x is going to be a 0. And the limit as x goes to infinity of 7 over x squared is going to be a 0. So we get infinity times 1, which would be infinity. So we're indeed not getting the 7. It looked like it might have been with that other faulty technique. We end up with the infinity over here. All right, so what really happened there was the only part that mattered was the lead term. The answer to this ended up being the infinity, but where did that infinity come from? It came from that lead term, which got factored out here and ended up right there, and times 1, and we ended up with that infinity. All right, now it's time to start summarizing some of the things that we've learned. So in this box, we're going to look at a summary of limits at infinity of powers, and then also of polynomials. So first, just a reminder of what we saw on the previous page. If you have n is an even number, so if you're going to have an even exponent and you look at the limit as x goes to either plus or minus infinity of x to a power, you always end up with an answer of infinity. But if it's odd, it's different depending on whether you're going to negative or positive infinity, because for those odd powers, the right side goes up, the left side goes down. So if we summarize the odd one, we need two different descriptors. The limit as x goes to negative infinity of x to the n would be negative infinity, but the limit as x goes to positive infinity of x to the n is going to be positive infinity. And then we want to take that from the previous page and then look at, like, well, what happened with the example up above? We were doing the limit as x went to infinity of a polynomial, but all we ended up looking at really in the end was just the lead term of the x squared. So we're going to take that idea and say, when we're working with a polynomial, really, if you're trying to figure out the limit as x goes to infinity of the polynomial, just look at the lead term to determine whether the overall polynomial is going to plus or minus infinity, and that'll get the job done. So why can we do that? A little bit messy in the notation, but when you're looking at the limit as x goes to infinity of a polynomial, that means you're looking at some a sub n x to the n, plus another coefficient times another x to a power, and it just goes on and on like that till you eventually get to your first degree term and then finally to some constant term. That's kind of the generic form of a polynomial. So what if you were doing the limit of all of that? Well, based on what we did in the example above, you could factor out an x to the n from that, and then have the other piece be inside, so you divide every one of these terms by x to the n, and you just get a to the n plus a to the a sub n minus 1 divided by x plus, and it would go until you get over here, and you would have a to the 1 over x to the n minus 1, and the last one would be a sub 0 over x to the n. Yeah, right, there we go. So now what happens when you take the limit as x goes to infinity of that expression? So the lead part goes to infinity, but this piece right here would go to 0. This piece right here would go to 0. This piece would go to 0. All the ones in the middle would go to 0 because all of those have a constant in the numerator and an x in the bottom. So what would be left over is just these two. So when you multiply it out, you end up just getting the limit as x goes to infinity. You could factor the constant out front of x to the n. That would be a to the n times the limit, which would be infinity, and you would just end up with infinity. So you can kind of judge it all just by the lead term. So this piece right here tells the whole story, however that turns out, and that piece just comes from right there. So from now on, when we look at polynomials and we're trying to look at the limit as x goes to infinity, instead of doing all this factoring stuff, which can be pretty messy to follow, we'll just be able to just focus on the lead term and use that to answer the question. So let's look at some examples where we kind of speed up the process by using that idea of it's the lead term that matters. So if I want to know what's the limit as x goes to infinity of 5x to the 7th plus 7x squared plus 1, it's just the lead term that matters. So I can say this is going to be the same as if I just looked at the limit as x went to infinity of 5x to the 7th. And that would be 5 times infinity, or just infinity. And come over here to the right, what's the limit as x goes to negative infinity of 5x to the 7th plus 7x squared plus 1? Well, it's going to be the same as if I just look at it for the lead term. So I can just ask the question, what is the limit as x goes to negative infinity of 5x to the 7th? So the 5 is a constant, I can factor that out. X to the 7th, that's an odd power going towards negative infinity. And when you have an odd power going towards negative infinity, you get negative infinity, and 5 times negative infinity is negative infinity. So I can simplify these limit to infinity or negative infinity problems by just focusing on the lead term according to kind of what's going on in this box, which is really messy, but we saw it kind of carried out in a specific example where you can factor out that lead term and all the other pieces end up going to 0. And so the lead term ends up telling the whole story. So later on when you're doing these, you can just put all your focus on just the lead term. All right, we've got a couple more examples here. And again, we'll do these quickly. We're taking the limit of some polynomials, so we can just focus on the lead term. The limit as x goes to infinity of negative 3x squared plus 2x plus 7. We can just put all of our focus right there and say, what is the limit as x goes to infinity of that piece? Well, you'd have the negative 3. And x to an even power going to infinity would be infinity, and negative 3 times infinity would be negative infinity. So nice quick answer there. And then practicing that one more time. What if we had the limit as x goes to negative infinity of x squared times x plus 2? You could multiply out the expression, or you could split the limit. Let's go ahead and split the limit. Either way would work. So we'll look at the limit as x goes to negative infinity of x squared times the limit as x goes to negative infinity of x plus 2. So on the first one, we only have one term. So, we're supposed to focus on the lead term, but there's just the one term, just the x squared. So we have the limit as x goes to a negative infinity of an even power. With the even powers, it doesn't matter if you're going to positive or negative infinity, the y value goes to infinity. Then we switch over to the next one, and for that one, we would focus on the lead term. So what happens to x as x goes to negative infinity? It goes to negative infinity. And if you take a big number times a big number, you get another big number, but if it's a positive times a negative, it turns out negative. So this would be negative infinity. And that's our answer. And then there's one other kind of weird thing we want to investigate to kind of tie all this together, which is what happens if you're trying to do this limit work and you're splitting up limits and you get infinity over infinity. Well, we saw on the previous page that if you got infinity minus infinity, you couldn't just say those canceled. You had to say, like, we don't know what happens. There's an attempt, maybe a temptation to say infinity divided by infinity would be 1, but again, we don't know that these large things are the same size. So we don't really know what happens there either, but we do want to be able to figure it out. So this next box talks about a process to help us do that. So if you're trying to find the limits at infinity or examine the end behavior of a rational function where the top and bottom are polynomials, what do? And the answer is, or the process is, determine the highest power of x that appears in the denominator. Not anywhere in the fraction, but specifically in the denominator. So I'll highlight that part. If you just look for the highest one anywhere, it can go a little weird. So find the biggest power of x that occurs in the denominator, and then factor out and cancel that value of x to the k from both the numerator and denominator. And then after you've canceled that out, you should be able to take limits and evaluate the rest. So that's step 3, kind of says, carry it out and see what happens. So let's try and apply that down to this example below. Let's find the limit as x goes to infinity of x squared plus x plus 1 over 3x squared plus 7x minus 3. So what's the largest power of x in the denominator? X squared. So I'm going to factor that out of the numerator and denominator. So limit as x goes to infinity, factor out that x squared in the top, or divide every term by x squared. The first term would become a 1. X over x squared would be 1 over x, and 1 over x squared on the last piece would be 1 over x squared. And then on the bottom, also factor out that x squared. 3x squared over x squared is 3. 7x over x squared, we get an x canceling, we get 7 over x. And 3 over x squared is 3 over x squared. And then what happens when we take the limit as x goes to infinity? Well, imagine splitting the limit up into all the different pieces. All these pieces that have constants in the top and x's in the bottom, they're all going to go away because they're all going to go to 0. So every one of those I just crossed out, what really is happening is they're all becoming zeros. And then these x squareds cancel out as well, so what's left? So all that's left when all that goes down is the limit as x approaches infinity of 1 over 3, and that's a constant, so the answer is 1 over 3. All right, so there's the first one. Takes a little bit of getting used to, so we will examine that further. But oh, by the way, before we go on, we just found that the limit of this function ended up being a constant. We said earlier, anytime that happens, it means you have a horizontal asymptote. So the horizontal asymptote for this graph is y equals 1/3. They didn't ask us for that, but we talked about that earlier, so it's good to see an example of that right here too. So there we go. Let's practice the stuff from the box a little bit more. So we're looking at another one. The limit as x goes to infinity of 4x squared plus 2x over 3x cubed plus 2x squared. And again, putting our focus on the largest power of x we see in the denominator, and that's what we're going to factor out of both the numerator and the denominator. So we're going to still look at the limit as x goes to infinity, but we're going to factor out an x cubed. Let's do it from the bottom first. That's a little more straightforward. 3x cubed over x cubed is just 3. 2x squared over x cubed, we get some x's to cancel and we get 2 over x. In the top, again, we're taking out the exact same thing. You don't factor out the biggest power of x from the numerator and the biggest power of x from the denominator. You find the biggest power of x in the denominator and factor that one out of numerator and denominator. If you do that here, 4x squared divided by x cubed ends up being 4 over x. And 2 over x divided by x cubed ends up being 2 over x squared. All the pieces that have a constant in the numerator and an x in the denominator, those three pieces are all going to go to 0 as x goes to infinity. And then these x cubes are going to cancel out. So what's left? When you evaluate the limit, you get in the numerator 0 plus 0, in the denominator 3 plus 0. Overall, that's 0 over 3, or just 0. So this graph has a horizontal asymptote of y equals 0. So here's the answer to the limit, and then that always results when you have a value as the limit goes to infinity of some constant. That constant gives you the equation of a horizontal asymptote at the same time. So one of the things that I like to do on these, I guess I'll do one more example, and then I'll show you a bit of a shortcut that I like to apply. So in the first one, the power of x was the same in the top and the bottom, the biggest power. In the one we just did, the bigger power was in the denominator, and in the last one, we have one where the bigger power is in the numerator. So we're going to kind of see the full scope there. So you're supposed to start off your focus, what's the biggest power in the denominator? That's that x. Factor that out from the top and the bottom. So look at the limit as x goes to infinity of, and then let's factor that x out from the bottom. That would leave 1 plus 1 over x. Factor that x out from the top. That would leave 3x plus 1. What can we cancel out? Those x's out front would cancel. This 1 over x doesn't cancel, but it would go away because it's going to 0. So what happens then as we take the limit as x goes to infinity? The limit of 3x as x goes to infinity is infinity. The limit of the constant 1 would just be 1. And in the denominator, you'd have 1 plus 0. So you have infinity plus 1, which is still essentially infinity, over 1, which is still essentially infinity. So we got three different situations that I'm going to show you kind of a quick note for. When the power of the top and bottom were the same, so that was our situation here, the biggest power in the top and bottom were the same, we ended up with the coefficients of those two powers, 1x squared over 3x squared, and that 1 over 3 ended up being our answer, 1 over 3. But when the biggest power in the numerator and denominator were not the same, and the bigger powers in the denominator, that ends up meaning that the denominator grows faster than the numerator, making the overall fraction go to 0. When you have the bigger power is in the numerator grows faster than the denominator, leaving an infinity up top and a constant in the bottom and an overall answer of infinity. So you can really get a very quick glimpse at where this is going just by seeing, are the powers equal in the top and the bottom, or are they different? All right, we're going to go into a little bit of side business here on this last one. When you're thinking about the asymptotes that occur, there's actually a very special case when the degree of the numerator is exactly 1 higher than the degree of the denominator. We get what's called a slant asymptote. So there's a line that the graph gets closer and closer to on both the far right and the far left, but the line's not horizontal, the line's not vertical, it's slanted. And if you want to get the equation of a slant asymptote, you got to do some work. And the work's not fun necessarily, but it is something we're asked to do. So let me show you the process. So we're trying to look for the value of the slant asymptote. So what you do is go back to the original problem. It's a division problem. We're taking 3x squared plus x, and we're dividing it by x plus 1. So I'm going to set that up as a long division and carry it out. So for a long division, we do some scratch work. We take the lead term underneath, 3x squared, divide by the lead term out front, simplify that, and that's the first term of our answer. And then we take that number up top and we multiply it by what's out front. So 3x times x plus 1 gives us 3x. squared plus 3x. And then we subtract that from what's above. And if we do that subtraction, 3x squared minus 3x squared is 0, and x minus 3x is negative 2x. That's not the end of the process, though. We still need to do the division again. So we go off to the side, we take the negative 2x, we divide it by the lead term out front, which is x. We get negative 2. That's the next term of our answer. And negative 2 times x plus 1 gives us negative, whoops, put that in the wrong spot, negative 2x minus 2. And then we take that and we subtract it from what's above. And if you do that subtraction, negative 2x minus a minus 2x becomes negative 2x plus 2x, which is 0. And the minus, the two minuses here, this minus and that minus, create a positive, and we get plus 2. And when you get to a point where what's left is smaller degree than what was out front, that what's left part is your remainder. So we would end up saying we have the remainder of plus 2 over x plus 1. And if you look at that and you say, what happens to that as x goes to infinity? This piece right here has a constant in the numerator, but the denominator is growing really large, so that part's going to go to 0. So as x goes towards infinity, we can say that the graph of the function is going to start looking like y equals this piece, which is the equation of a line. So the graph should be approaching y equals 3x minus 2. Nobody loves long division, but if you want to figure out the equation of a slant asymptote, it's long division that gets you there. And if we're going to do all that work, I think we should see that it's actually true, that the graph is approaching that line y equals 3x minus 2. So let's go ahead and switch over to the calculator and see if that does indeed come through for us. So let's go ahead and get out of this graph, go into the y equals. So we're going to put in the original function, 3x squared plus x divided by x plus 1. Notice I'm putting parentheses around the numerator and denominator to make sure the whole numerator is getting divided by the whole denominator. And let's just go look at that graph first of all. So there it is. I can only see part of it, so I'll zoom around and we can start to see more of it. So notice first of all that the original thing we said was that as x went to infinity, the y value goes to infinity. And notice it does look that as x goes to the right, the y value keeps going up. And if I zoom in even more, I can see that continues to be true. So x gets bigger, y gets bigger. So that kind of justifies our overall answer of infinity that we gave. But now can you see how on the far right that this looks kind of straight? And over here on the, let me move the graph around, over here on the far left, that also looks kind of straight. So the claim is that that straight line it looks like is our slant asymptote. So let's go back into the y equals and add the equation of our slant asymptote. We'll do that in red. So what do we come up with there? 3x minus 2. Let's look at that graph again. And notice how, not in the middle, but over on the far right, it looks like you're getting a blending together of the green and the red, which means that green is approaching the red. It's getting closer and closer without touching. They're not quite the same, but if I trace on the red, now that seems very close to what the green is. And the same thing way over here on the left. So that slant asymptote is a line that on the far right and the far left, our graph is getting closer and closer to without touching. The without touching is not a requirement of an asymptote, but it is common. All right, so slant asymptote is a bit of a messy deal, so it's not what you're rooting for. Your least favorite situation should be when the degree of the top is exactly one higher than the degree of the bottom, because that's the situation where you get slant asymptotes. If the degree of the top and the bottom are the same, you get a horizontal asymptote, and that's not so hard. If the degree of the denominator is bigger, then you get y equals 0 as a horizontal asymptote, not so bad. It's only this bottom case where the degree of the top is exactly 1 higher than the degree of the bottom where the slant asymptote comes up. All right, we're going to go ahead and continue on and look at a few more examples of limit at infinity, or limit as x goes to infinity. And unfortunately, these get a little bit tricky. So buckle in, and here we go. So what do you do if you have the limit as x goes to infinity of x squared over the square root of x to the fourth plus 1? Well, intuitively, it should just be the lead term that matters, right? So if you thought about that, you have an x to the fourth here and an x squared there. And at first you might go, okay, the bottom is the bigger number, so it's going to grow faster. And if the bottom's bigger, the overall thing will go to 0. But wait a minute, it's not x to the fourth in the bottom, it's the square root of x to the fourth. And the square root of x to the fourth is x squared. So maybe the top and bottom are actually more the same. So what we want to do in this situation is somehow get some reducing to happen so we can clarify what's going on. So what I'm going to do is I'm going to divide the top and the bottom by x squared. So I'm going to say I have the limit as x goes to infinity up top, x squared over x squared. And in the bottom, I'm going to divide all of this by x squared. But that x squared is not inside the square root. But I've done the same thing to the top and bottom, so that should work out okay. So now what happens when I do that? It's still the limit as x goes to infinity. Up top is nice. We have x squared over x squared, so that's just a 1. And in the bottom, I want to somehow kind of get that x squared inside of the square root. So I kind of think to myself, like, all right, so if I put it inside, what would it be? So what is it that I could put right here so that its square root is x squared? And the answer to that is x to the fourth has a square root of x squared. So that x to the fourth inside the square root is the same as that x squared on the outside. So we don't usually try and move stuff in the square root. We're used to moving it out. But in this case, it's useful to move it in because now I can say I've got that 1 up top, and in the bottom, I'm looking at the limit as x goes to infinity of, and I can break this into 2 fractions. I have x to the fourth over x to the fourth plus 1 over x to the fourth. And all of that, sorry, you're going to have to squeeze this in, so I'm going to do it in a different color just so we can see it. All of that's still inside of the square root. All right, so what happens with those pieces? Well, if you started kind of applying the limit to all the different pieces and evaluating, what happens? Well, let's go ahead and simplify it a little bit first, and then we'll do that. So we'd have 1 over, we're taking the limit as x goes to infinity, and we have the square root of x to the fourth over itself, which is 1, plus 1 over x to the fourth. Now let's take this limit right here and apply it to both pieces inside. And then we'll just do the evaluating. So on top we have a 1. If we take the limit as x goes to infinity of 1, that's still a 1. If we take the limit as x goes to infinity of 1 over x to the fourth, because the top is a constant and the bottom is growing big, the overall thing goes to 0. We get 1 over the square root of 1, which is 1 over 1, which is just 1. So a little harder to see it at first and a little harder to make it work. You're still kind of focusing on the biggest power in the denominator, but you got to think about that idea that, like, okay, there's an x to the fourth in the bottom, but it's really the square root of x to the fourth. So that's what we're trying to work with in both cases. All right, that's kind of a messy idea, so let's look at it again and see if we can get some more clarity. And I'll approach it slightly differently this time too. So let's go back to that idea of, let's look at the biggest power in the denominator, or the kind of lead term down there, and it's this 9x squared. But it really is the square root of 9x squared, or you could even say it's just you don't need to worry about the 9, just the x squared. So what if I divided top and bottom by the square root of x squared? What would happen there? So we're taking the limit as x goes to infinity. And on the top, I'm going to take x plus 2 and divide that by the square root of x squared. And then I'm going to do the same thing on the bottom. Square root of 9x squared plus 1 divided by the square root of x squared. So what is the square root of x squared? Well, when x is positive, and x is positive here because we're approaching positive infinity with the x, so that tells us that x is positive. When that's the case, the square root of x squared is x. So what are we looking at? We're looking at it in the top, x plus 2 over x. And in the bottom, instead of simplifying the square root, I'm going to combine the two square roots. So I get the square root of 9x squared over x squared plus 1 over x squared, kind of distributing this x squared to both terms of the numerator. And I can combine them under one square root because they're both in the square root already. All right, so this is pretty messy, but we're almost there. Now we can start doing some simplifying. We have the limit as x goes to infinity. And then in the top, we have x over x plus 2 over x. And in the denominator, we have the square root of 9x squared over x squared plus 1 over x squared. And then let's just start looking at what happens to each of those pieces. What happens to this piece, this piece, this piece, and that piece as x goes to infinity. So for the first one, it's x over x, so that's just a 1. The second one is a 2 over x, so as x grows large, that goes to 0. In the denominator, we have the square root, and then the 2x squareds will cancel, and we'd still have the 9. And the 1 over x squared is going to go to 0 because the top is a constant and the denominator is growing. So in the top we have a 1, in the bottom we have the square root of 9. So overall we have 1/3. So that's the same idea as above, but I looked at it slightly differently. On the first one, I just went ahead and divided top and bottom by x squared and then tried to figure out how do I put that underneath. Maybe a little on this different take might be one that more of you process better, is divide by the square root of x squared, top and bottom, and then it's a little easier to think about how that all combines up. Either way works. I've done it both ways, but I think this second way is going to carry over better into our final example. So let's take a look at this one. So if you look at it, it's actually the same problem as before. The limit as x goes to infinity of the same exact fraction, except for it's not x goes to infinity this time, it's x goes to negative infinity. So we just need to think about, is there anything different because of that? So we're going to start off very much on the same path. Let me go ahead and just draw a little separator here. So we're going to look at the limit as x goes to negative infinity. And just like we did last time, we're going to start off dividing the top and bottom by the square root of x squared. So you'd think this is going to the exact same answer, but it doesn't. Spoiler alert. And the reason it doesn't is because of a little known fact, something you don't think about very much in pre-calculus. But if x is going to negative infinity, that means that x is negative. And it turns out that the square root of x squared in general is not equal to x. It's equal to the absolute value of x. We just always look at it in pre-calculus for positive numbers. But, if you take the square root of negative 3 squared, you don't get negative 3. It's the square root of 9, which is the absolute value of 3, which is 3. And if you're taking the absolute value of x, sorry, I'm going to break your brain a little bit here, but if you're taking the absolute value of x when x is negative, you have to change its sign. Here was a value that was negative, and the absolute value made it positive. But what you really want to think of is the absolute value switched its sign when it was negative. This x is negative, so the absolute value will switch its sign. So again, prepare your brain to be broken, but sometimes the square root of x squared is negative x. And the when that happens is when x is negative. And in this problem, our x is going to negative infinity, so x is negative. All right, so we take that brain-breaking knowledge, and when we take the square root of x squared and we simplify it, we say that's x plus 2 over negative x. And these we just combine up like we did before. So that's going to be the square root of 9x squared over x squared plus 1 over x squared. And then we start simplifying. Let's build a wall here. So in the numerator, let's do our limit first. In the numerator, we have x over negative x, so that's negative 1 minus 2 over x, moving the negative out front there. In the denominator, we have the square root of 9, and then plus 1 over x squared. And when we apply the limit to that, those pieces with the x in the denominator end up going to 0. So this goes away, that goes away. What's left? Well, in the numerator we have negative 1. In the denominator we have the square root of 9, which is 3. So our answer is not the same as it was before. We get negative 1/3 instead of positive 1/3. And what does that allegedly mean about our graph? Well, if x is going to infinity, that's what's happening on the right-hand side of the graph. Apparently, this graph will have a horizontal asymptote of y equals 1/3 on the right. But as x goes to negative infinity, the limit is negative 1/3. So according to that, this graph should have also have a horizontal asymptote of y equals negative 1/3, but that's only going to happen on the left as we go to negative infinity. Can this craziness really be true? Let's go see. So we'll go to the graphing calculator. We will put in our function. So clear out this old stuff. So our numerator is x plus 2. In the denominator, we have the square root of 9x squared plus 1. Let's graph it. We got this kind of crazy picture going on here. Let's do zoom standard to get into our negative 10 to 10, negative 10 to 10. Well, look at this. The right and the left are not approaching the same height. So we'll kind of tweak it a little bit to see it in a different view. But look, the right-hand side is positive, and the left-hand side has dropped to be negative. Now let's go out further and see if it looks like it's 1/3 that it's approaching. As we go way out on the right, the y value is showing up as 0.338. That looks like it's approaching 1/3. If we go to the left, negative 0.327, that looks like it's approaching 1/3. We can go out further. 0.337, closer to 1/3. On the left, negative 0.3329, close to negative 1/3. So this weird thing with the square root that I showed you, where sometimes the square root of x is negative, if we didn't do that, we would have got the wrong answer on the left. And we can see from the graph that asymptote on the left really does need to be negative. So that all hinges on this idea that the square root of x squared is not always x, it's the absolute value of x. And in the case where x is negative, that means the square root of x squared is negative x. So you have to remember that when these come up. Otherwise, you'll get the wrong limit and therefore also the wrong asymptote. That's about as messy as it gets for this section. There it is. I hope you survived okay. Ask some questions when we hit the collaborative time if you need some more clarification, or hit me up during office hours. All right, after the previous page in that last example, you'd think you'd been through enough and I would let you stop, but we got one more page and it has one more messy example. So probably should have been parentheses there, so I'll go ahead and add that in. Hopefully that'll be there on your handout by the time I make some edits. But the limit is of that whole quantity. And if you just plugged in the infinity right away, you're going to end up with like an infinity minus infinity situation, which we already said before is not necessarily 0. So we don't know what that is by like a quick plug-in. So we need some sort of trick that can help us get to a place where we can sort this out. How do these balance out, the addition and subtraction of these two infinities? So one of the tricks that's common with a square root problem when you have a subtraction or an addition is to try and make the square root go away and have some things cancel. And that all hinges on something from factoring in algebra, the idea that a minus b times a plus b is equal to a squared minus b squared. So that's your difference to square formula. And if we can make that apply here and we end up through that process squaring each of these pieces, it could make the square roots go away, and then maybe we get some cancellation and make some progress. So what we're going to do is try to apply that. We've got the minus case here, so we already have this part, so we want to introduce sort of out of thin air this other part, the same two things but with a plus, so that when we multiply them together, we end up squaring both parts and getting rid of the square root. So here goes. I'm going to take the numerator of this, and I'm going to multiply it by the exact same thing that we have already, except it'll be a plus in the middle. And that's going to make this difference of squares piece happen. But you can't just take something and multiply the numerator and not change it. So what you have to do is multiply the denominator by the same thing. Well, the denominator was a 1. So I'm going to now multiply that denominator by same thing I introduced in the top. And temporarily makes things look a lot messier, but it gets better. So we still have this limit as x goes to infinity, and in the top, again, this is another brace yourself moment, but this is a times a, so we should get a squared. And if you square a square root, you get what's inside. So we're going to have for the a squared piece, the square root, the thing I just highlighted in green squared, which will be the inside part, x squared plus x. So that's my a squared. And then we're going to have from our formula over here a minus sign, and then we want b squared. And the b portion is going to be this piece and that piece. And when you square that, you get what's inside. So that would be x squared plus 2x. So that's my a squared right here, and my b squared right there, following from that formula. And in the bottom, there's no multiplication going on, so I'm just going to copy that down. So square root of x squared plus x plus the square root of x squared plus 2x. All right, so then what ends up happening with all of that? Well, in the numerator, you get some simplification. Let's go ahead and carry that on over here. So you get the limit as x goes to infinity. The x squareds cancel, and then you have x minus 2x, which would end up being a negative x in the numerator. And for the denominator, those are not the same, so I can't really simplify it much. So for the moment, I'm just going to copy it. And now I'm going to try and apply that idea we did before, where I want to divide everything by the largest term in the denominator, which is the square root of x squared. So I'm going to continue with the limit over here as x goes to infinity and divide top and bottom by the square root of x squared. So negative x up top, square root of x squared underneath it. And then I'm just going to do that division. I'm going to do that on just every single term. So I'm going to divide that, and that all by the square root of x squared. So I'm just going to move that right into the square root immediately to save some writing. So we have square root of x squared over x squared plus x over x squared plus a new square root where each of those also gets divided by x squared. And then we start thinking about what happens as x goes to infinity. All right, well, first of all, x is going to positive infinity. So why is that important? When x is going to positive infinity, that means the square root of x squared is just x. We don't have to change the sign because the inside piece wasn't negative. All right, now because we're starting to run out of space, I'm going to start evaluating the limits. So what is the limit as x goes to infinity of this piece? So let's look at the pieces one at a time. The limit of, first of all, the square root of x squared is just an x. So that's negative x over x, which is just negative 1. So the limit of the numerator is just going to be that constant, negative 1. As we go down to the denominator, what about this piece right here? Well, x squared over x is just a 1. So that's the square root of 1. And then How about this piece? Well, the denominator has a bigger power of x than the numerator, so that one is going to 0. And then same thing in the next two. Do those a little quicker. This piece is going to 1, that piece is going to 0. So we get another 1 plus 0. So what do we end up with? Negative 1 over the square root of 1, which is 1, plus another square root of 1, which is 1. So 1 over 2, which is 1/2. So there's another trick that you can apply sometimes. You hope you don't see it too often because it is messy. But if you have this infinity minus infinity situation where a square root is involved, try multiplying by what we call the conjugate. If you start with the minus, multiply by the plus. If you start with the plus, multiply by the minus. It'll usually be a minus because if it was two pluses, the infinities would add up. It's when it's a subtraction, you get the infinity minus infinity, which is undetermined, and you need to wrestle with it to get to an answer, which we did. You can graph this one too, by the way, if you want, and you'll see that y equals 1/2 is a horizontal asymptote for this on the right-hand side, because we only looked at limit as x goes to infinity. All right, one final one, and this one's not so bad. It's a nice, easy one, actually, to finish off with, but a bit of an application. The population of a culture of tumor cells is given by the P of t equals 3,500 t over t plus 1. What happens to the tumor cells in the long run? So as time goes to infinity, what happens to the number of tumor cells? So it's just a limit question. So we want to look at the limit as t goes to infinity of 3,500 t over t plus 1. Well, we have the same power in the top and the bottom, so those should kind of essentially cancel out, and it's only the lead terms that matter. So 3,500t and the t are all that matters. As t goes to infinity, that plus 1 just doesn't make it much of a difference anymore, so it should be 3,500 over 1, those two coefficients divided by each other, and have an answer of 3,500. I'll show you the math on it one more time, though. Divide everything by t in the top and the bottom. So look at the limit as t goes to infinity of 3,500 times t over t, all over t plus 1 over t. Take the limit of the individual pieces. After you think about cancellation, these t's cancel, those t's cancel. So where do we end up? In the numerator, we have 3,500. In the denominator, we have right here, that's a 1. And then 1 over t, if t is going to infinity, is a 0. So the overall limit is 3,500. And then what do you call that if you have like this thing that's changing, but in the long run, it reaches a limit? In an application like this, sometimes we would say that this means this system has reached a steady state. So there's an application of this idea of looking at the limit as the variable goes to infinity. Not a very cheerful one since it's about tumor cells, but there we have it. At least they're reaching a steady state at some point instead of growing without bound, which would be bad for the host. All right, that finally wraps up section 2.5. I hope you made it.